Hello. Um, Today we're looking at symmetry. The basic idea behind symmetry is that when we look at a graph of a function, let's say I have, for instance, this graph right here, I can say that there's some kind of pattern to this graph. Okay, not drawn to scale, but I guess close enough right here. And that pattern right here in particular is that, let me try redrawing it. That pattern in particular is that the two sides of this graph right here look the same but are opposite to each other. but opposite to each other. Right here. The dividing line in this case right here is the y-axis. And that y-axis right here is what we call the line of symmetry. So, this graph is said to be symmetric with respect to the y-axis right here. And whenever a graph is symmetric about the y-axis, it holds certain basic properties. The most basic property is, first and foremost, it looks like the y-axis is cutting in half. So visually speaking, right here the y-axis cuts into two halves that are mirror opposites to each other. And the second property right here is that if I take any point on this graph, say 3, 4, there must exist a graph opposite to it, i.e. its mirror opposite with the coordinates -3, 4. Because it's mirror opposite, it's not exactly the same, and what changes right here is one of the signs on the coordinates. The basic rule is this: for every point x, y, there must exist a point -x, y. If that happens, then your graph is symmetric with respect to the y-axis. Again, the way I remember this right here is if I'm looking for y-axis symmetry, it is the x-coordinate that must change signs. If I'm looking for y-axis symmetry, it is the x-coordinate that must change signs. And that is because we're jumping over the y-axis. If I'm jumping over the y-axis, notice that the height stays the same. If the height stays the same, then the y value stays the same. But clearly, my x values are switching sides. So this is 3 right here, and that's -3 right here. And so therefore, my graph right here is symmetrical about the y-axis. Similarly, if I have a graph that looks like this, and a graph that looks like this, call this the ukulele graph, I guess. And this graph right here, again, kind of looks like the same graph right here. This time it is the x-axis. That's the dividing line that's splitting in half. And so this graph, from visual inspection, we can say is symmetric with respect to the x-axis. Similarly, if I have a point on this graph, let's take this point right here, 2, 3. If my graph is symmetric with respect to the x-axis, then there must be a mirror opposite point on the other side of the x-axis with the coordinates 2, -3. Every point on this graph must have its mirror opposite friend. Once this happens, see right here, I have a mirror opposite friend down here. Once this happens for every single point, we say the graph is symmetric with respect to the x-axis. And in mathematical terms, we write for every point x, y, there must exist a point. There must exist a point x, -y. What's happening right here is that the y values are changing signs. Again, if you look very carefully between these two symmetric points, you'll notice that they have the same x value. But it is the y values that are changing signs when you jump over the x-axis. Again, the same rule holds. If I'm looking for symmetry with respect to the x-axis, it is the opposite letter that changes sign. Now there's one more kind of symmetry that often boggles the mind. Say I have a graph right here, and I have a graph right here. A graph that looks something like this. This graph right here is said to be symmetric with respect to the origin. The mirror is actually a single point right here at this point right here. If I have a point on my graph, say 2, 8, then I must have a mirror opposite point normally on the other side, and this point right here will have coordinates -2, -8. Notice right here that when I go through the origin, I move from one quadrant over here to the other quadrant, and to move from that side to the other, both signs must change. And so that leads us to the basic rule. For every point x, y, if I am symmetric with respect to the origin, then there must exist a -x, y. The visual inspection is a little bit harder when it comes to the origin. But the way you do it right here is that you take half the graph, and then you first flip it over the x-axis. Well, over that actually doesn't matter. Flip it over the y-axis, and then flip that over the x-axis. And then the answer you get right here should be the other half of the graph. If you have that, then your graph is symmetric about the origin. Now, the problem that we have with symmetry is that sometimes we're not given the graph of a function. I know. And so we have to determine symmetry algebraically using algebra. So, for example, let's say I have the expression y is equals to x to the 4th power minus 6x squared plus 2 right here. And I'm trying to figure out, well, is this graph symmetrical about the x-axis? Is this graph symmetrical about the y-axis? Is this graph symmetrical about the origin? Well, I have to actually check each of these one at a time. I'll explain why in a second. But yes, the graph can have one-on-one symmetry. So let's go ahead and try y-axis symmetry first. Remember that if I'm looking at y-axis symmetry, then every xy, there must be a -x, y. And so what you do is you plug in -x, and then you simplify. If you plug in x and then simplify, you should get the original equation back. So I took out my expression right here. I go y is equals to, I plug in -x, I raise it to the 4th power, minus 6, I plug in -x, I raise it to the 2nd power plus 2, right here. So I replace each x with a -x, and then I simplify. And so y is equals to, well, what's -x to the 4th power? That's going to be a positive x to the 4th power. And -x squared is again just x squared plus 2. And what I note is that this answer right here is exactly the same as the original problem, exactly the same as my x, y. And so that means the graph is symmetric. To the y-axis. Let's go ahead and try x-axis symmetry. And as a reminder, every xy I must have in existence a x, y when I'm looking for x-axis symmetry. And so what that means is I'm going to plug in negative y and then simplify. And then I'm going to ask myself, do I get the same problem that I started with? So I plug in negative y, and that's x to the 4 minus 6x squared plus 2. I have to simplify, so I multiply by negative 1. And I get that y is equals to negative x to the 4 plus 6x squared minus 2. This is the negative version of the original, so it's not the same. So it's not the same as the original, and therefore the graph is not symmetric. About the x-axis. I know, really sad, right? I know. But that's alright. The last one we need to check is the origin. Again, recall, for every xy, I have to create a negative x comma negative y for my origin. And so I have to plug in, can you guess? Both negative x and negative y, and then simplify. And so that will leave me with negative y is equals to negative x to the 4th minus 6 to negative x squared plus 2. And so that's negative y is equals to x to the 4 minus 6x squared plus 2. And just like before, I have to multiply by a negative 1. And I get the same issue I had a while ago. This is not the original problem. And because it's not the original problem, it's not symmetric to the origin. Oh boy. So, my graph right here has only one symmetry, and that symmetry is that it's symmetric about the y-axis. The last thing I want to point out right here is that if I have the graph of, say, for instance, a circle, very beautiful circle, I know. This graph right here has actually all three symmetries. My equation is x squared plus y squared is equals to, say, 64, right here. If you check all three symmetries, x, y, and origin, you'll see it has all three. If I make the x-axis the middle, I get 2 halves, the y-axis, and so forth and so on. This is all three symmetries, which indicates that a graph can have more than one symmetry, and that's why we have to check each symmetry one at a time. On the other hand, I could have a graph that looks like this, and this graph right here has no symmetries. Again, the reason why you need to check all three is because it's possible to get an answer of none as well.